Hello, we are Team BME, and our group members are Bright, Miles, and Edrian, and our project is Visualizing Duke Architecture.
Hi, this is Adrian. Now, before looking at this image, did you know that there exist beautiful arches surrounding the ceilings of the numerous walkways here at Duke? Some of you most probably have not, and that is what our project was for, to showcase the beauty of arches on West Campus. Our client, Dr. Edward Triplett, is working on a project that aims to make Duke's Gothic Revival architecture more visible. The project focuses on visualizing Duke's architecture in the context of a digital map with an ArcGIS online 3D scene where 3D objects are placed on their exact locations. These 3D objects are generated using a complex process called photogrammetry. It basically takes images or scans as input and 3D models as output, with processes like image matching, feature extraction, triangulations, etc. in between. Our goal was to create a device that holds the camera while taking pictures of the arches, which are often 10 to 15 feet tall. Professor Edward Triplett found his previous solution, a painter's pole alone, hard to use and inaccurate due to the lack of stability while taking pictures, causing them to get blurry. Thus, our design challenge was to produce a more stable device for Dr. Triplett that allows him to take pictures of Duke's arches easily and precisely.
Our design had to meet 4 different design objectives. It had to precisely tilt, rotate, and adjust the height of the camera. It had to be portable and storable. It had to be easy to use, and it also had to be inexpensive. Our final prototype had 4 main components. The first component was a base made out of 1.5-inch diameter PVC pipes, and attached to the corners of the base were wheels, which are labeled as B on the picture. The second component was a coupler, which was 3D printed using polylactic acid, and the coupler would hold the extension pole in place and keep it tight and stable. And the extension pole was the third component, which is labeled as part D on the picture. And this component would extend up to 10 feet, and it extends using the button, which is labeled as E on the picture. And the fourth and final component was the camera holder, which was tiltable and rotatable, and it was attached to the top of the extension pole.
The base of our device is built out of PVC pipes, which are low cost and sturdy materials. The pipes are placed in a square formation, and there are 2 supporting pipes coming from the base at 45 degrees, and these supporting pipes are secured by a 45-degree all-hub coupler. Using 1/4 inch nuts and bolts, a caster is attached to each corner of the base to easily move the camera holder from place to place. Each has a brake which stops the device from rolling down slopes. And with the casters, the camera holder can be precisely rotated to any angle, which is one design criterion of our project. The extension pole is a 10-foot long painter's pole with a button that releases a lock when pressed to allow the pole to extend in certain height increments. To fasten the pole to the base, we 3D printed a removable pole tightener. We ensured that this part is a perfect fit for the pole and the PVC pipe and is easily removable to fulfill the portability/storability design objective. The camera holder is a ball-joint tripod camera mount that has a pistol grip which controls the tilt and rotation of the camera when attached. The position is firmly held when tilted or rotated, keeping the camera still when taking photos at different angles. We also use a painter's pole adapter to attach the tripod camera mount to the painter's pole.
This is Bright Abua. In the next slide, you see a video of our final prototype's demonstration, from its setup to its movement to everything about its usage. So just click the image you see there and you see the video of how our prototype is used.
Our device is called the camera holder, which is made of 1.5-inch PVC pipes with wheels and couplers, one holding our camera pole in a steady position, as you can see in our video, Before we use our device, we fix the camera pole into the coupler, and we also fix the camera onto the camera pole to scan an arch as high as the one you can see in our video. And this is what one of our members is doing in the video. After fixing our camera, since we'll be extending our camera pole to a very high altitude, we need to connect our camera to a certain app which will allow us to take pictures high above the arch. That is the second stage of setting up our device, and in this application we can change the focus, we can change the brightness, we can change almost everything and every setting in the camera. We added wheels to our base so that we can be able to move our device to many locations. As you can see, we've moved our device from its original position to a different one, and our PVC coupler is very tight that it allows us to also move the device in different heights without the device disconnecting from our base, and that's why we chose that coupler. And our PVC base is also strong to support our camera pole. Not only that, we can also change the pan and tilt of our camera by pressing the grip on our camera holder on the pole, and we just have to press our extension button to change the height, and we are done. We just have to take pictures on our phone whenever we change the height. Our device is very steady, and very stable, and that's what our
In testing, our device passed all tests for portability and storability. So the total mass was under 10 kilograms. It was 6.7 kilograms. And it was also detachable into 3 parts, and each part weighed less than 4 kilograms and measured less than 4 feet. It also passed all tests for ease of use. So the mean time taken to assemble the device by users was 4.1 seconds, which was under our design criteria of 30 seconds. And the mean rating on the user-defined scale was 5, which passes our design criteria of 3.5. And it also passed the test for inexpensiveness. And the total cost was $110.70, and our design criteria was $150. Our design also passed the test for tilt, rotation, and height increments. The camera would tilt 20 degrees, it would rotate around 360 degrees, and it would also increment in increments of 3.5 inches. However, it did not meet our design criteria for the height, which was 10 feet, and it missed the mark by 5 inches.
These are the 3 3D models that we scanned throughout the semester. As you can see in the first model, there are many missing spots and gaps in the model, indicating that we did not take enough pictures and we missed many angles while scanning the arch. For our next 2 scans, we took more photos and made sure we got every angle of the arches, and the models were much more accurate. This is also because we used Metashape instead of ArcGIS to create the 3D models, which turned out to be more advanced and easier to use.
So in conclusion, our device provides enough stability to support a camera at heights up to 10 feet to take pictures to make 3D models. This allows for scanning in suboptimal situations such as low light settings because of the added stability for the camera. However, our device does fall short since it does not reach structures higher than 10 feet, and it can be difficult to use on uneven surfaces. To address our shortcomings, in our future work, we could extend the device to heights up to 15 feet by implementing a longer painter pole, and we could also work on developing a mechanism to allow the device to be used on rough or uneven surfaces. And to make our base sturdier, instead of using PVC pipes, we could use carbon fiber poles, which are stronger and more lightweight, but more expensive. And finally, we could integrate the 3D models into 3D maps and add those maps onto the Duke Digital Art History and Visual Culture website. And finally, we would like to extend our gratitude to all people who helped us throughout the engineering design process for this semester. Thank you.